Welcome to the technical lecture from NCTS. This is second in the series of three lectures from Mr. Athavale on basic metallurgy and inoculations. And today's subject is basic metallurgy for SG After completing the Master of Engineering program from Indian Institute of Science, Bangalore, specializing in foundries sciences in 1980, Mr. Athavale joined Mrs. Foseco India Limited. During his tenure with Foseco, he gained hands-on experience in developing products for various applications in ferrous and non-ferrous foundries, and worked as product head for coatings, coal dust substitutes, filters, and inoculants. He retired as head of technology and marketing. Mr. Athavale has presented papers at seminars of Institute of Indian Foundrymen and other industry associations. He has co-authored an educational paper on the refractory coatings for ferrous and non-ferrous applications for NCTS. He continues to work as consultant for technical training as well as marketing. I now request him to take us through his presentation. Thank you.
What we will cover today is, we will once again revisit why people buy castings and then go towards SGIN, understand what is SGIN and how carbon forms into graphite nodules. Then we will go to the steps in SGIN casting production process. Then magnesium treatment is one of the key for getting spheroids. So what are the different techniques that are used for doing the magnesium treatment and merits and demerits of these different processes. We will then look at the important aspect of inoculation of SGIN, but I'll spend only a short time on that because in our third lecture next week, we will cover inoculation in detail. We'll also look at a few slides on solidification behavior of SGIN and need for proper feeding to get sound casting, because SGIN has a distinctly different way of solidifying than gray iron. Gray iron, very rarely you will require any feeding because carbon which comes out of the solution compensates, because it's low volume, it compensates for any shrinkage which you have. And very, very briefly, I'll talk about different types of SGIN and their applications. So that is what I intend to cover today. My first slide, which I had used last time also, what do casting buyers buy? They buy dimensions, properties at a particular cost. Dimensions are governed by mold and core. Microstructure is decided by the way the metal solidifies. It not only applies to cast iron, it is for any metal which is solidifying, or for that matter, any material which is going to microstructure. And production efficiency decides the cost of making it. And buyers are always looking for lower costs for getting the same specifications. Really, the service requirements and functional requirements of the component decide from designer's side what should be the microstructure, what should be the dimensions. I've chosen, as some of you would, or all of you perhaps would recognize, is a steering knuckle, a component used in automotive industry which is part of steering system. This diagram shows a drawing, a 3D drawing of steering knuckle, and all these points 1, 2, 3, 4, 5 indicate what are the different linkages to which this knuckle is connected. Now, what is the role of steering knuckle? The role of steering knuckle is to convert linear motion of tie rod into the angular motion of the stub axle. So it has to be strong, it has to be inflexible, and as much lightweight as possible. When the steering is turned, half portion of the steering knuckle component is subjected to tensile load. The other half is subjected to compressive load. And due to the rotation of the wheel, steering knuckle also is subjected to torsional load. And last but not the least, it also supports the vertical weight of the wheel. So it is being subjected to all sorts of stresses, and it is a safety critical. Like steel forgings, ductile iron or HC iron, aluminum alloy forgings are the options that the optional materials that the buyer has, and cost becomes the deciding factor. Now let's look at what is HG iron. We'll see a brief history, then a couple of slides on how graphite forms in the form of spheroids or nodules in the iron matrix. Because I'm not going to cover the iron carbon diagram and different pieces. We have already discussed it in our gray iron lecture. A very brief history. Gray iron is brittle with almost nil ductility due to carbon precipitating in flake form. So malleable iron was the option which offered ductility because carbon is present in the form of spheroids or nodules after lengthy heat treatment cycle. Now search for iron with graphite in nodular form in as cast condition was being done in UK by BCIRA as well as in USA by INCO separately in early 1940s. And INCO announced HG iron formation by magnesium treatment in 1943, and they took a patent on it in 1949. Let's look at what is the graphite growth mechanism on a nucleus. And this is a crystallographic picture of graphite, which is hexagonal close packed. So two close packed basal planes, 6 prism planes. Growth will take place that means on top of the lowest interfacial energy. That means direction of growth will be perpendicular to that plane. Now, in normal course, basal plane being closely packed, more closely packed than the facial planes, has got the lowest interfacial energy. So, logically speaking, if everything pure, that means purest of the iron, that you add pure carbon, melt it in vacuum and cast it in vacuum, what you will land up will be iron with carbon solidifying in the form of nodules. That is what happens in the experiment in the laboratory. However, in reality, our cast iron has many other things like oxygen dissolved in it, it has got sulfur, it has got nitrogen. Now, let's quickly look at what happens because of presence of these surface active elements. They get absorbed on the high energy plane, which is vertical plane. So that reduces the interfacial energy of that plane below the basal planes. So any growth happens at right angles to that lowest energy plane. It is happening on it. So growth takes place on 6 sides rather than basal plane and finally forms the planes. Now, in case of spheroidal graphite, what happens after you remove the oxygen, sulfur, nitrogen? The nodulizer that you use for treatment neutralizes surface active elements. Now the basal plane has got the lower energy and the growth takes place on top of the basal plane, that is, and the growth happens in the direction at right angles. So a spherulite is formed. Now this is as far as graphite is concerned. If you take eutectic composition, then this picture is pretty clear. You have got these graphite nuclei in the liquid and you have this primary austenite coming out. And these are dendrite arms, and you'll find some nodules are being trapped within those, in the liquid between the dendrite arms. And as the solidification progresses and the eutectic grains are growing, you'll find that the nodules get entrapped in this solidifying matrix, and this is how it looks. B shows the picture of a fracture of ductile iron and a nodule nicely sitting there. And this is the microstructure of ductile iron as we see at lower magnifications. Well, this is from electron microscope. This was the graph, this was the picture we had seen last time in glia iron. So I have put a red colored grid around what is happening on desulfurized hypoeutectic ions and the effect of cooling. Not only graphite has come out in the form of nodules, but if the cooling rate is moderately fast, then you will get pearlitic ductile cast iron or pearlitic ferritic, while if it is slow cooling, you will get ferritic ductile iron. Now, what are the steps in HDI casting process? And here is the generic process flow. You take raw materials, you do the melting, do the adjustments by doing analysis. There is liquid iron. If sulfur is on a higher side, you do desulfurization, and then you treat the iron with magnesium. Magnesium removes sulfur and oxygen and converts, and the nodularization happens. That means the nuclei, the carbon which is precipitating out forms nodules. And then you do what we call as post-inoculation to ensure that there is good graphitization happening. So get the iron ready, get the right temperature, pour it in the molds. Then usually in ductile iron, you will do two-stage inoculation. So one just when you're prior to magnesium treatment or halfway through the magnesium treatment if it is possible. And then you do the stream inoculation or mold inoculation to ensure that the inoculation effect doesn't fade. Do the quality treatment. If there is a heat treatment which is recommended or required, you do it and supply the casting. So that's the generic process flow for ductile iron casting. Let us now look at the heart of this process of making ductile iron, which is magnesium treatment. This is one of the pictures which I have picked up from CDC, and they also have taken it from Centricast in their publication. So as you increase the magnesium content into the melt, how gray iron structure changes. The graphite from flake goes to compacted graphite or vermicular graphite as it is also called as, and then it goes to ductile iron or spheroidal graphite iron. So as the magnesium content increases, the mode of the form of graphite changes. So you move from gray to compacted graphite to spheroidal graphite. So a typical production cycle would be start with low sulfur iron less than 0.015, desulfurize if necessary the base iron, add magnesium with the aim to dissolve around magnesium of 0.25, and total magnesium depending on how much are the losses will be 0.35 or 0.45. The difference is present as oxides and sulfides. Magnesium, part of it also will get vaporized. Magnesium also promotes iron, it's a strong carbide stabilizer. So generally you will, the base ions for HDI production would have higher levels of carbon and silicon, and you will need stronger inoculation. So inoculate with powerful inoculant. So that is a typical metal treatment process. Now, what are the methods for adding magnesium or doing magnesium treatment or nodularization of the graphite? So what is key is we should have an effective and predictable use of magnesium. So variety of methods are available. all of them aiming for giving this predictable results and high yields for magnesium. So magnesium reacts with sulfur present in liquid ion until residual sulfur is around 0.01%. Once sulfur reaches this level, then the magnesium has very little effect on graphite formation. Then magnesium goes in solution. Now, how much magnesium gets tied up with sulfur? You need about, for every 1 kg of sulfur, you would require about 0.75 kgs or 76 kgs of magnesium. I have given it here in percentage. And people define the magnesium recovery as magnesium recovery percentage is equal to 0.76 into sulfur percentage in base metal minus sulfur residual percentage that you get from analysis, residual NB percentage and magnesium percentage added. So magnesium recovery is lower at high treatment temperatures and is dependent on particular treatment process that is being used. One question which was asked to me by one of my friends was, what about the effect of oxygen? The oxygen in iron is variable. It keeps on changing. For example, in induction furnace, in research papers, they have found 30 to 80 ppm, in cupola 70 to 150 ppm as it comes out. But it drops very substantially on holding. So as the regular production cycle moves, there is lot of fluctuation in the oxygen level in the ductile iron. So normally you take care of this unknown by making some allowance while you do the calculation. What are the different nodularizers which are used by foundries? It is magnesium ferrosilicon alloys, magnesium in the range 3 to 20. Very rarely people will exceed 10%, very rarely. Nickel magnesium alloy 5 to 15%. Then pure magnesium is used in the form of ingots or wire, cold wire. Or sometimes people have used magnesium iron briquettes. They are compacts of pure iron and magnesium cold wire. Now, if you look at very approximately what is the composition of ferrosilicon mat, say for 5% magnesium and 10% magnesium alloy. So silicon around 44 to 48. Magnesium for 5% will be in the range of perhaps 5.5 to 6.6, or 10% could be around 9 to 10%. There is calcium 0.2 to 0.6 in one case, 0.5 to 1 in another case, rare earth elements, then aluminum, which will come out of your ferrosilicon magnesium products. And rare earth contains roughly about 50% cerium. We call it as mesh metal when it is used separately. Calcium is added normally to reduce the reaction violence and enhance magnesium recovery. Here is a table which shows the effect of rare earths on the nodularization. Instead of going through the table, I'll only say that presence of rare earths increases the nodule count, as you can see from this data from an experiment done in the labs. What are the different methods of nodularization? It can be ladle treatment being done in ladles. Also, sandwich, we'll look at what this sandwich is with ferrosilicon mat, or use of a converter which uses pure magnesium, or use of a chamber which also uses pressurized neutral gas along with plunging of pure magnesium, You can have cold wire, again with pure magnesium, or you can get magnesium plus maybe some other elements like ferrosilicon sitting there, or in mold treatment of ferrosilicon magnesium. We'll look at these different types of nodularization one by one. Here is a rather crude picture of what happens in ladle treatments. So the one here is where it's an open ladle. In one corner you have put alloy and you have covered it with some punchings and you pour the metal on top of it. In sandwich, it is a little more sophisticated. You have created a pocket at the bottom, and the pre-calculated amount of your nodularizing alloy is kept in the pocket, and it is covered with either steel punchings, or sometimes people use ferrosilicon itself. While some cases, I have seen this particular process, the third one, where the pocket is sealed with, I have seen it being sealed by sodium silicate bonded sand. And then after the metal has been poured, the pocket is opened by poking it with a bar, a crowbar, and allow metal to react with the treatment alloy. The most popular one and perhaps most effective one is this. In this case, you have got a tundish cover on the top, so that the ladle is closed, and the opening of the tundish is such that the metal first also on the other side away from the pocket, and then the metal level is built rapidly, and then the alloy starts reacting with it, and in the same way a slight variation in the lock. Now let us look at what are the improvements in the magnesium recovery. Moreover, in sandwich and in ladle with the tundish. In pour over, depending on how well you are running it, 40% or sometimes less than that recovery. In sandwich, 50%, 55%, but open ladle. While you go to tundish, which is closed ladle, the recoveries can be as high as 65%. Here is a picture of a typical ladle. You have got a brick separator here at the bottom. You can see it is red hot. You have put the ferrosilicon mag alloy. Now, as you can see, once you have put the brick at the center, there are two parts which are created. So they are used alternately, so that the slag that is generated as a result of reaction doesn't block only one. So it helps keeping this pocket clean. Then the alloy is covered with this fine steel punchings, and you get nice proper treatment done, good recoveries. And here is a chart which shows the design for treatment ladles as well as conditions for variety of treatment sizes, going from 500 kgs all the way up to 2000 kgs. I'm sure they are available in literature many times. Now, what are the most important points for good magnesium recovery? A height to diameter ratio of the treatment ladle of approximately 3:1. A lot of you would say 3 looks high, because in literature you will see 1:1.5, 1:2 as being pretty common. But I have seen with higher H/D ratios, because the magnesium vapors have to travel through a taller column of metal, the effectiveness of the treatment increases. If time allows, later on I can share one of my experiences in a very specialized foundry making small ductile iron castings for automotive industry with a very small requirement. I think treatment size was something like 120 or 150 kgs, but the H/D ratio there was very high. It was 5:1. The whole plant was set up for that. And the arrangement was such that they did not have to worry about the what we call as fade. We'll talk about magnesium fade later. And the whole pouring used to get over within about 4 to 5 minutes. Then the control tapping of metal from furnace to the ladle, that means you should not have interrupted pouring there. It is very important to build the metal level over the magnesium in the pocket as rapidly as possible. At the same time, maybe finding out a way of putting the sort of ferrosilicon mag in between, which serves as full stage of inoculation as well. They are large lumps. Then another very important point is the size of the ferrosilicon mag lumps and the amount of fines which go with that. Because the fines will burn off very, very quickly. So having a good control over the grading of ferrosilicon magnesium lumps is very crucial. I had come across experiments done when I was working with Persico, and we had seen that a good control over ferrosilicon mag lumps for different ladle sizes. It depends on the size of the ladle, quantum of metal you are treating. Then quality and placement of alloy covering like steel punchings. That also is very crucial because it is the steel is going to take away some of the heat from the metal and it is going to lower the temperature. Adequacy of the covering of the treatment ladle when you are putting the tundish. So it has to be properly put and properly sealed so that you get good recovery. Let's look at in-mold magnesium treatment. This is a very specialized form and it is used for castings which are mass produced. Very large numbers. One type of casting in a layout. So what it has is the magnesium treatment chamber is put inside the running system itself. The design of the reaction chamber is done through experiments to begin with. The aim being that you should be able to get uniform pickup of magnesium throughout the pouring cycle. An adequate amount of magnesium should be picked up from the alloy in the reaction chamber. Now, because this is part of the mold itself, everything is sitting inside your mold on top of the mold. There will be a lot of slag generation, so you need to take care of the slag. One, by using some sort of a filtration device in your running system, ensuring that it doesn't become the choke. Then have a tall runner bar in the core, and then take your ingates which go into the mold cavities at the bottom of the bar so that any slag which has not been trapped will either be sitting in the top portion of the bar because it is light in weight, or this runner bar extension, and cleaner metal will go through. One advantage is that you can this has to be designed for a given casting. Everything has to be designed for a single type of casting and its layout on the pattern. No capital equipment is required for magnesium treatment. I know the yield will be reduced because the running system is heavy. You have a chamber and but then you have the other advantage of not having the capital investment at all. I had seen this in 1 or 2 foundries in India, but I've seen it 3 or 4 times in Matsushita foundry in Singapore, where they were using this in-mold treatment for production of crankshaft used in steel compressors. Ductile Iron crankshaft used in steel compressors. So it's an item which it is very tiny, very small. The service requirement are such that it is machined all over. Not a speck of sand is tolerable. machining allowances were very, very tight in this case. And they have been using this extremely successfully, producing lakhs and lakhs of these crankshafts. So whatever modularizing element that you are using, ferrosilicon granules, or whether you are using the tablets, what you see here are different types of vessels and methods which are used for using pure magnesium for treatment of liquid iron. Here what you see is a plunging bell. The other one that you see is the magnesium being blown through the bottom. It would be put through a nozzle at the bottom. The third one, which I have seen at one or two foundries here in India, like Tata Motors Marvel Foundry, where the ladle of liquid metal is put inside a chamber, it is sealed, and pure magnesium is plunged into it, and there is a covering of neutral gas in the chamber. The bottom one here uses a diffuser, while perhaps the most popular one is the converter, which was designed by George Fisher. And the last one that you see is a rotary ladle, where you have a chamber here in the and where you put your treatment material. Long ago, Foseco had tried magnesium impregnated coke as a material for doing this rotary ladle treatment. Let's quickly look at the George Fisher converter, and I'm sure many of you would be very familiar with this. You place magnesium in the chamber here, treatment chamber. Take the liquid metal when the converter is in horizontal position, close the lid, rotate the converter to a vertical position. The treatment takes place maybe in 60 to 80 minutes, 60 to 90 seconds. And then open the lid, rotate the converter back and take it into the pouring ladle. Generally, during the first part, initially first deoxidation and desulfurization happens. Later, magnesium gets dissolved. Magnesium recovery rates of up to 70% are seen regularly in this. Base ions with 0.2 to 0.3 sulfur are readily treated. Temperature loss of about 20-25 degrees is seen in 1 ton converter. As the converter size increases, the drops will come down. Even the recoveries may go even higher than that. I think George Fisher would have designed converters going all the way up to 20 tons perhaps. And another big advantage is, since there is no silicon added in the charge by way of ferrosilicon mag, it's pure magnesium treatment, there is no limit on the use of returns. The third next process that uses pure magnesium, sometimes magnesium with something else, is cold wire. As you can see here, there is a spool of cold wire here. The wire is hollow mild steel tube which is filled with magnesium powder and is guided through a guiding tube into the ladle which is covered. So it leads into a close fitting through the close fitting lid into the molten metal. Various tube diameters are available, say ranging from 4 mm to 13 mm. Tube dissolves inside the iron and releases magnesium. So relatively, because the release is happening slowly, the reaction violence is less, and anyway it is sealed. There is a cover on the top. The feed rate of the coil is decided by the amount of sulfur, the temperature of the metal, and what is the composition of the mix which is being used in wire. So I said the reactivity of the wire. The feed rate can be programmed after finalizing all the treatment parameters into the computer. Just as an example, typically for a 9 mm wire, a feed rate which is about 30 to 50 meters per minute is required for 1500 kg metal treatment, and treatment gets over in 2 minutes at a temperature of 1450 degrees centigrade. I have personally seen this code wire technique at a couple of foundries, one in South, and I have seen one with Tata Yodogawa, the ductile iron pipe maker near Jamshedpur, where this was being used for treatment of blast furnace iron, which was then cast into ductile iron pipes. Now, quickly, a table which gives comparison of ferrosilicon mag and pure magnesium as neodymiers. Now, low magnesium content generally between 3 to 10, though earlier I had indicated maximum 20. So, higher additions are required in terms of quantity to get desired residual mag, which is very obvious, while pure mag requires lesser additions. The reaction violence tends to be a little lesser with ferrosilicon mag as compared to pure mag. That's why most of the pure mag processes you will have an enclosed vessel. So closed or enclosed vessel like converter or pressure chamber for plunging or wire feed, while simpler treatment vessels like ladle or ladles with 10 dish cover are enough here. Base metal with low silicon and low sulfur is needed for ferrosilicon mag treatments using induction furnace or doing duplexing, while base metal with higher silicon and sulfur can be tolerated. So preferred by foundries which have large productions. So cupola melted base metal, say hot blast cupolas, or like for ductile iron pipes from the blast furnace itself. Smaller treatment sizes are possible with ladle, while treatment sizes here tend to be larger. I think the smallest converter I have come across is 1 ton. Ferrosilicon mag chemistry and grading are the variables, and they add to the process variation, while in pure mag there is no chemistry variability. So that one variability is less there. Then, as we have seen the operations of a typical ladle operation for treatment, there is a lot of manual operations and manual skills involved in getting a consistent result, while pure mag processes tend to be far more mechanized. To that extent, the reliability and repeatability of the process is better. Magnesium recovery rates range from 40 to 60% depending on the quality of the materials, the upkeep of the equipment, while the magnesium recoveries up to 70 or sometimes even more than that are possible in pure mag process using converters. Capital costs are certainly lower for ladles. Maintenance costs also are lower, while in case of converter-like things, the capital costs are high, the maintenance cost is high. It is suitable for different sizes of foundries, small or medium, while the converters because the capital cost is high, so it is used mostly by medium and large foundries and DI pipe makers, like I said. A large tonnage needs to be handled. Now let me come to important aspect of magnesium fade, because it is not only enough to put the magnesium inside, we have to see what happens next. The magnesium fading, that means the magnesium which has been picked up and dissolved in the metal, it doesn't remain there. Magnesium vaporizes. It has got a boiling point of 1091 degrees C. So the losses are two ways: evaporation of the magnesium as the vapor travels through the metal column and goes away, and oxidation. The oxygen can come from slag, it come from pores in the lining or from the atmosphere. Another thing happens, magnesium sulfide particles, they race to the bath surface, they react with oxygen from the air and magnesium oxide forms. Sulfur gets released and diffuses back into the melt. So again bond with magnesium, and this cycle repeats. That's why earlier I commented about importance of keeping the treatment vessels clean. Then handling of the treated material can speed up the magnesium fading because turbulence happens, the fresher surface gets exposed. So from treatment vessel to the pouring ladle, so when the multiple transfers are happening, turbulence occurs and the oxidation takes place, loss to the atmosphere happens. The fading leads to undesirable graphite shapes. We had earlier seen at the beginning of this lecture a slide of magnesium content in the liquid iron and how it transitions from gray iron to compacted graphite iron or vermicular iron to Ag iron. So the reverse thing happens. As the magnesium level drops, the graphite structure and shapes change. Now, let me come to the next important part of the process, inoculation of Ag iron. Now, magnesium treatment is violent. The nucleation level in the magnesium treated iron is low. Plus, the magnesium itself is a strong carbide stabilizer. So, to get proper graphitization, large additions of inoculants, 0.5 to 0.75% are needed. The inoculation effect also fades quickly. So, usually two-stage inoculation is done. Initial inoculation is done halfway through the magnesium treatment, or sometimes you may put it earlier in the your treatment vessel before the tapping happens. But otherwise, after the magnesium flare is reduced, you can add it. Coarser grade of inoculant is used. And final inoculation, 0.1 to 0.2%, can be done in late stream or it can be done in mold inoculation. The inoculation application rates, of course, will vary depending on how powerful the inoculant is and where it is placed. So, just to give an idea, if uninoculated iron is solidified, then you will see here the free carbides. You see these needles. While inoculated iron, you see here is ferritic pearlitic structure at 40 magnification. Now here are micrographs from nuclei from inoculation. We find that the particles which are at the center of these graphite nodules, in this case the barium-based inoculant was being used. So they served as a substrate on which this nodule has grown. Now whether ferrite or pearlite will form, and I don't know whether you are able to see, I think if you are seeing it on the screen you will see this. See, smaller and more the number of nodules, you will, or you can get coarser graphite nodules if your inoculation or nucleation levels are different. Good nucleation levels, you will get many nodules, but smaller size. While if you are low level of nucleation, then there will be less number of nuclei, but bigger nodules. What is the effect? The formation of ferrite structure is favored when you have more nucleation levels, because graphite finds it, carbon finds it easier to go to the nuclei which are nearby. While as the number of nuclei become lesser and lesser, then you will get coarser graphite nodules and you will get ferrito-pearlitic, some ferrite and some pearlite. While the nucleation level drops further, then you can get coarse graphite nodules and more pearlite and lesser ferrite in your microstructure. Now, a small slide. See, throughout our gray iron lecture as well as this lecture, what we are saying is, if you want to manage the microstructure and hence the properties of the iron. You have to manipulate chemistry, composition, magnesium treatment, and nucleation levels and cooling rates. I am saying chemistry and composition separately. By composition, what I have in mind is actually the charge makeup. The charge makeup also carries its own inherent nucleation levels. Now, these will decide nodule count, nodularity, and matrix, and hence the mechanical properties. Here is a picture, and unfortunately, I was not able to get a clearer picture than what you are able to see. I'm not very happy with this. But it is a picture which is taken from Ductile Iron Society's papers to show how the different microstructures are going to give you different grades of iron. So you have a ferritic grade here, which as per ASTM classification you have, it is called 60-40-18, 18% ductility or elongation. You have 60,000 psi UTS and 40,000 psi will be your yield. When you have ferritic pearlitic grade 80-55-6, now with more pearlite, your ductility has dropped to 60, your yield point has gone up to 55,000 and ultimate tensile at 80,000 psi. In pearlitic grade, which is 173, the ductility has dropped to 3% elongation. Then your yield and ultimate strengths have gone up substantially. You do the heat treatment and you get tempered martensite and you'll get a strength which is even higher. And you move towards ADI, then the strengths go even austenitic ductile iron, which have been transformed in. So two more higher grades. This graph, what we saw in microstructures and figures there, as you can see, ASTM A536 and then ASTM A897, that was for ADIs. But down below here, if you see ferritic ductile iron giving you higher elongation and tensile strengths, which are megapascals here. As you move towards ferrite and pearlite combination, then the ductility elongation has dropped, but the strength has gone up. And as you go towards pearlitic microstructure, the strengths are even higher, but the elongation has dropped. And then in between you have this zone where you have tempered martensite, and then you get into ADI. So this covers the microstructures of various types of ductile ions. Now here are a few tables which I have picked up from CDC data. This is reproduced from Cosico Founderman's handbook. And it gives you different grades. Like we covered the American specifications here. The equivalents are given as European or UK. So different strengths in different units, newtons per mm square and percentage ductility here. And what kind of typical structures you get. So the same information but in tabular form for different standards. And here are some suggested analysis, chemical analysis for as-cast production of ductile iron when different average casting section thicknesses need to be produced. So less than 13 mm going all the way up to greater than 100 mm section thicknesses. So you have first grouping where you have pearlitic ductile iron, then pearlitic ferritic, and then ferritic grades here. See, the major difference will be, as you would see, is in the amount of manganese that you are using, because that is a strong pearlite stabilizer. And to an extent, some amount of silicon, but otherwise not much difference in that area. And obviously that's the main difference really. You use manganese extensively for control of the microstructures. And other requirements like phosphorus less than so much, chromium less than so much, and a rather big range of 0.3 to 0.6 for residual mag is given. That's because we are covering all the section thicknesses. And there is a note here which says that for higher grades, that is 800, 700, 600, some amount of copper or tin would help perlite formation. It will refine the perlite as well. Charge composition, I don't have to say much really, but people will use different proportions of foundry return, steel scrap, pig iron with low sulfur, and various other additives like ferroalloys and graphite and ferrosilicon. For ferritic ductile iron, use of pig iron in the charge is absolute necessity because you need high level of nucleation for producing ferritic ductile ions. Now, very briefly, the feeding of ductile iron. Why SGIN requires feeding? They have high carbon equivalent, so the volume of graphite precipitated during solidification should have ensured complete soundness, like what happens in gray iron. But here, the expansion resulting from graphite precipitation here in case of ductile iron generates very high pressures on mold walls. So for gray iron, compared to gray iron, it's much higher. As you can see, the numbers are given here. So strong molds, very strong molds, as chemically bonded molds like sodium silicate sands, very well vibrated loss foam molds, they will resist the pressures and you'll be able to use very little feeders or special cases, feederless SGIN casting, but they are really special cases. Otherwise, use of feeders is very common in ductile iron castings. I'm not going to get into details of the methoding. There is a separate, actually, there can be a separate conversation on that. Here are some common ductile iron applications: crankshafts and hubs and steering knuckles and diff cases and calipers and large windmill hubs and so many. Thank you.
I now take this opportunity to thank Mr. Athavale for a very informative lecture on SGN. He has covered everything from process of nodularization, steps in production process, various treatment techniques. I'm sure everyone attending today's lecture must have recollected what he has learned during his college days, and this definitely will help in our day-to-day working. Thank you everybody for attending today's lecture.